Hello.
Hello, sir.
Yes, it came now. It took such a long time. Is it because of the Red Sea cable cut that it is taking such a long time? Okay. All of you are able to hear me clear, loud and
Yes, sir.
clear?
Yes, sir, we can hear you.
Great.
Yes.
Yes,
Okay.
sir.
Good evening, guys.
Good evening, sir.
If you have any doubts on this topic, on the subject that is going on, design and simulation of power converters using open source tools. Okay, let me know. One thing that you can kind of contemplate is that, see, these open source tools keep changing. The idea is open source tools. Different versions also keep coming. At the time when this was recorded, I had used ngSpice for simulation, and ngSpice even today is quite powerful, and you have a lot of upgraded libraries, and the version of the ngSpice is also much higher, and much powerful engines is available, and you can simulate much more complex circuits, blocks, schematics. So depending upon which version you are using, you can get familiarized with that. You can also see, the concept is that you want to learn the circuit. Okay, you can also use other open source tools like LT-Spice. LT-Spice is also a freeware. You can try using that, and also familiarize yourselves with the outputs and study the circuits. Only thing is, in the case of the LT-Spice, it is not the code is not Spice compatible. The netlist is not the original Spice compatible netlist. It has its own proprietary netlist, so you need to get used to that kind of a proprietary netlist. Okay. This apart, you are free to kind of explore in any open source. The reason why I say open source, because the title of the topic, title of the course is based on open source tools. So therefore, I am kind of emphasizing that you can use any open source, but it should be open source. Any tools, but open source. Okay. Other than that, the course is kind of focusing on power converters, and that's what you would be going through, different types of power converters and how you go about simulating. So one aspect is you should try to understand what these circuits do. Okay, one hand. The other hand, you should know how to put those circuits into a framework which can be simulated by ngSpice. ngSpice is a very, very powerful environment, just like MATLAB is an environment for all your computations and block schematic oriented simulations like Simulink. The ngSpice is a very, very powerful circuit simulation environment. Okay, it's very, very deep, has a steep learning curve, but once learned, there are a lot of things that you can do out of that. So this is the background, and this is the background and intention of the course, and use the simulation to make the design. So once you have simulated, the various waveforms indicate will indicate to you what is the maximum value of the voltage, what is the maximum value of the current. Based on that, you can decide the ratings of the components that come in a particular branch and node, all those things. So it will aid in the design of the circuit. So this is the basic core fundamental objective of this particular course. And hopefully you have got this aspect right? Any doubts that you have, write in the chat box or you speak up and let us know so that we can talk on that. Well, how do you find the course? Is it hard? Anybody? We're all very silent. Supposed to be interactive session. You need to open out. Tell me, was it difficult? Is it difficult? Have all of you got the hang of ngSpice? ngSpice is such a powerful tool. See, among all the simulation tools that are available, the reason we chose ngSpice is that it is the deepest. It is the one which has the maximum flexibility. It may not be the most user friendly, but it has the maximum maximum functionality and depth. It is composed of three major components. Spice itself, the original Spice coming from Berkeley, the Berkeley Spice. Then it has Cedar as another component that is integrated into ngSpice. And a third component that is integrated to ngSpice is XSpice. All these components deal with circuits. It also deals with analog behavioral models, which basically is something that you can use for doing block diagrams too. If you are having models, you can do block diagrams too. So this is something very special and powerful aspect of ngSpice. If you have delved deep into it, you will see that it's an ocean. A lot of things you can keep learning. Okay, will you please explain the hill climbing method and insulation concept? Okay, hill climbing and insulation concept, why should it come in this part of the course? This is a power conversion course, not the photovoltaics course. But still, anyway, I will explain to you. See, you have a hill. Okay, the hill is representing your function. So any function that is in the shape of a U or in the shape of a V or inverted. It could be a U or an inverted U, V or an inverted V. Then it obviously means that there is a minimum value or a maximum value which I can find, which will be the optimum value. So when I say it's a hill, it's an inverted V or an inverted U, and you are searching for the max. How to go and settle at the max value. So that's what hill climbing algorithm would mean. One of the ways is that you keep on moving to the right or left. And if I see that my gradient is positive, then you keep on moving in that direction till you go over the hill and the change in gradient. Okay, once there is a change in the gradient, you make the reversal and again go over the hill. At the same time, you should have some plate which keeps on very slowly moving up. So let us say that ball or you who is moving up the hill and down the hill at a much faster pace will hit the boundary wall, which is the plate moving up gradually, and it will restrict your movement at the top. And as the plate keeps moving, your movement at the top will keep on restricting till your movement is in the narrow band of the hill peak. So then we say that you are in the neighborhood of the peak of the hill or at the maximum point. It's used in the maximum power point algorithm and photovoltaic systems. But why did you ask that in this particular course? Because this is a power conversion course involving design and simulation. But anyway, that is the concept. Okay, there is another question from Arun. I am attempting to model a coupled inductor based DC-DC converter in LT SPICE. I noticed that using the SPICE directive KL1L2, modeling the mutual coupling between the inductors with the coupling coefficients. However, in the literature, authors often represent the coupled inductor as magnetizing inductance in parallel with an ideal transformer, specifying Ln and the turns ratio. While trying to relate the two approaches, I derived the expression L1 is Lm plus leakage, and this one, and mutual inductance is this one, where leakage is the LLK is the leakage inductance relative to the primary. Is this formulation correct, or is there a more accurate or recommended way to model coupled inductors in LT SPICE? Yeah, if you are looking at LT SPICE, modeling magnetics is limited. In ngSpice, because of the analog behavioral modeling, you have great flexibility in modeling the magnetics. See, you will not be able to model the hysteresis. See, several of the problems that arise is because you like the model that you said, K L1 L2, where K is the coupling coefficient. It doesn't give a model where hysteresis component is inbuilt, and many of the real magnetics work because of the hysteresis component that is there. So you will get a very idealistic kind of magnetic circuit, which is okay for a crude simulation or a simple simulation. But when you want to actually take care of leakage inductances and the storage of energy in the leakage inductances, this may not be so accurate. Okay, but if you are going for between the two approach, I would prefer the latter approach, where you are specifying the mutual inductance and the leakage inductance separately, where leakage inductance is a component indicated in the circuit, which also will store energy, and to that extent you will be having non-idealities coming in, and when the circuit is being simulated, you will see all those spikes, LDI by dt due to leakages, which will get reflected even in LT SPICE as it happens in the as it happens in the laboratory experiment. So it will be a closer simulation, closer to the practical real aspects if you choose the latter model. Is that clear? Arun?
Yes, sir, it is clear.
Yeah. Because in week 4 assignment, there was a question based on it. Okay. Based on LT SPICE. I would not have mentioned LT SPICE at all. Why do you say that?
Sir, it's based on no, sir. It is based on actually the earlier concept.
Okay. The mutual inductance. Okay, mutual inductance and the leakage inductance.
No, the hill climbing method. There was a question on the hill climbing method and MPPT.
In
week
the
4.
Okay.
In week 4, and that's why I'm asking.
That's why you asked that one.
Yeah.
You understood the hill climbing, what I mentioned just now?
Yes, sir. Yes. Now it is understand.
Yeah. Anything, any other questions? Be free to ask the questions. Akshit is asking something. I have simulated an equation-based model from week 1 lectures, but I am getting an output as shown in the image. You help me in analyzing the problem here. What is the circuit that you have simulated? Akshit, can you tell what is the circuit that you have simulated? I see that you are having a step response, green colored step response, and you are having a damped response to the step input. What is the circuit? It depends upon what circuit you have. Actually,
Hello, sir.
Akshay.
Sir, it was RLC circuit, which was modeled by equation.
Okay.
So I am getting multiple outputs. So that is what I was seeking your suggestion on it.
That's what you are using a series RLC circuit, right?
Right, sir.
And you are seeing the voltage waveform across. You are seeing the voltage waveform across which component? Akshit? Akshit, you are off.
Yes, sir. I am not sure it is between input and outputs or output resistor, load resistor.
The step waveform is the input, is it? Hello?
Yes, sir.
Yeah, you are giving an input step, and then the RLC circuit is resonating. It's a damped resonating, depends upon the Q factor. It depends upon the omega, it depends upon the L and R, omega L by R, or it will be depending upon C and Q, or C and R. So depending upon the value of R, it is going into damped oscillations. Okay, if you kind of keep reducing the value of R, it will go into full resonance, and
Yes, sir.
isn't it? So it's a typical behavior of a series RLC circuit. Okay.
Yes, sir.
So this was simulated in LT Spice, is it?
No, sir. It is a octave.
You did it in Octave. Okay.
Yes, sir.
Okay. The equation-based model. Yes. Yeah. So the output is consistent with the theory. Actually, you should try to understand what it means by based on where you are tapping the output, which output are you tapping? Are you tapping the voltage or the current? Of course, it is going to be a resonant kind of a circuit with some damping ratio as you fix by the value of the resistance R. You can also try to get insight by having a circuit equivalent and then simulate it in SPICE. That also will give
Yes, sir.
you some insight. I see a lot of people are using LT SPICE. Why is it that people feel comfortable with LT SPICE than NG SPICE?
Sir,
Is there any particular reason?
Sir, we started with ngSpice, but later, when you have shown gsham for creating the schematic file, I was using Ubuntu, when I tried that to install
Okay,
GSM, it was not
you,
working.
you can, okay, you need not use GSHM for creating the schematic. You can use KiCad also. The front end, see the front end for writing the schematic, okay, I'd use GSM, that is the GEDS open source tool GSM. You can use KiCad also. Have you heard of KiCad?
Yes, sir. For a PCB design.
For PCB you do, right? You write the circuit schematic and then you make the PCB, right?
Yes, sir.
After you do the circuit schematic in KiCad, if you go to the export and the export netlist, it will be a netlist exactly compatible for ngSpice. You don't need to do any further editing. It can just directly run on ngSpice. You can use that also. You don't need to be limited by not having GEDA or GSHAP. Is that clear?
Yes, sir. Yes. Sir, one more query regarding that coupled inductor.
Yes.
So you have suggested ngSpice for doing that. So shall I?
Because you see, did you look at the models which I gave you in ngSpice for doing the magnetics? You have you simulated the forward converter or the full bridge converter or something like that one? Push pull. Did you do that?
In LTSpice, I have tried. ngSpice.
Yeah. No, in the ngSpice, I kind of demonstrated on the lecture video, right?
Yes, sir. But that link was not working. One
Is
a
it so?
library of files that sir has hosted in your website that was not.
That because that particular server crashed, and I have actually asked them to post that particular resource file into the resource directory of your course file. So it will be available in the resources directory. Have a look at that. Have a look at that magnetics. This one part of the library. You will see that you can really make complex models in ngSpice, and it may not be easy to do in other proprietary versions of Spice like LT-Spice or P-Spice or any other Spice. You have to kind of make do with what they offer, like your coupling factor L1, L2 model kind of thing, the basic coupling kind of model. That is why I keep saying use ngSpice, because it is very, very powerful.
This time I'm doing myself because of the confidential matter. Created two.
Yes. Is it clear what I was saying? Who was that question? Arun, is it?
Yes, sir. It is clear.
Yeah. So you can use LT-Spice. Only sometimes you may get limited if you want to do custom-based models. Whatever models they give in their library, yes, that is fine. It will work beautifully well. There is no issue. But suddenly you want to have a custom model, the flexibility in ngSpice is much greater in such cases. You can really make complex systems. You can see at the model that I used in ngSpice, you can have hysteresis also built into it.
Hello, sir.
Yeah.
So I have recently shared an image of a photovoltaic cell circuit made in the KiCad tool. So could you please review it? Is it correct?
So you have, it is so small, no, I'm not able to, let me see. It is appearing so small. 1 second. Let me download that. Okay. See, I1 is I1 is a current source, and what is why have you given that form of a current source shape? 0, 1, and then at 50 nanoseconds it is 1, 51 it is 1, and then as time progresses it is falling down. Is that it?
Yes, sir.
Right? Why have you chosen such a current source?
So because in GSCAM you have used other source whose best alternative I thought it
Because
will
if
be
you
there.
take, see, the model is like this. The current source I1 is a constant DC value, right? It is representing the sunlight. It is representing the sun intensity, what we call insolation. Agreed? So if you take at a given point in time, okay, where the sun is at some particular position above your place, the current here, current I1 should be a DC quantity, right? The at D on the output side where you have put a sine source. So that sine source is basically to see that the output voltage is swinging. The output voltage is swinging from 0 to 0.85. That is fine. And as the output voltage swings, what happens to the current? So when you are measuring the current at the output, you will see a falling current because of the presence of this diode, where part of this DC current will go into the diode characteristics comes into play. And then see, for example, if I say R series is 0, R shunt is infinite, then you are talking of diode coming directly across the output. So as the sinusoidal voltage varies between 0 to this one, the diode is seeing a variation from 0 to 0.5. And as it becomes more forward biased, you will see more current that it will draw. Okay, you will see the diode characteristic getting replicated at the output.
Yes, sir.
Okay. So the current here at I1, you keep it at DC. Don't make it vary for a particular value of sun position. Is that clear?
Okay, sir. Sir, and the diode 194007 is okay, or any other diode we have to use?
That is okay. It is a very commonly available diode. It has a 0.7 volts cut-in voltage. That is still okay. That doesn't change the general character of your output wave shape or the IV characteristic. But that diode actually is the internal PN junction of the PV panel. In a here for simulation you are using 1944007, but in a practical situation it is the internal PL junction of the PV panel.
Oh, Okay. Thank you, sir.
Okay. What is the most complex circuit you simulated during the course? Did you guys simulate the full bridge with the secondary side push-pull, diode O-ring, inductor, output capacitor, all those things put together? Did anybody simulate? Did anybody simulate closed looping operation, current control? You should try that. They are very, very interesting topologies for simulation and good learning circuits to learn. So, was it Akshit? I was mentioning. So, you have now used KiCad to make this, right?
Yes, sir.
And were you able to convert it to netlist?
Yes, sir.
In KiCad, if you go to the file menu, you will see that there is an export option, right? And there is an option to export to netlist. If you try that, that netlist that it generates is directly compatible with ngSpice. You can just directly call it in ngSpice.cir file and it will execute that.
Yes, sir.
Okay, there is also in KiCad a simulation tool which also uses the an ngSpice engine. You could use that also. But somehow I find that tool is very limiting compared to the ngSpice environment. I like to have the command line kind of access rather than GUI based access. But you can get a GUI based feel if you use the KiCad simulation tool. And you can set the simulation engine to be ngSpice.
Yes, sir.
Right? You tried that?
Yes, sir. I have tried.
Yeah. Which one did you feel comfortable? The command line or the GUI based?
Sir, command line is a more detailed version, we can say.
Yes.
More,
But you'll
more.
have to, you'll have to remember it may not be friendly, but command line is more powerful than the GUI based.
Yes.
So, anything else you guys want to tell, mention? Is the course difficult? Is it understandable? It is an old recording, of course. The tools keep evolving, changing. You should use the most modern version of the tools available from the internet. Download it and then use it, install it. How many of you are using Linux? Are you using Linux or Windows? Both. Dual boot, is it? I used to use Windows before, but my students got me converted to Linux. And now I don't feel like going back to Windows. Linux is so powerful and so surprisingly friendly. People think that Linux is not friendly. You need to only do command line and things like that. It is not like that. It is very very friendly and more. The GUI is more interactive than what it used to be on Windows. So I will definitely encourage you to try and shift to Linux after the more recent news of people trying to cause fear of like just what happened on the Azure cloud, right? Linux, you will not have any such problems, and you don't have virus problems also. So I will encourage you to try shifting gradually to the Linux mode. Do we use a demagnetization inductor at the input side in the flyback converter? So in the flyback converter, you will not use a demagnetization inductor. Only in the forward converter, there is a demagnetization inductor necessary. But in the case of the flyback converter, the load itself is the demagnetization part. So because you see that the dot polarities are opposite in the case of the flyback converter. So when the switch is on, the energy charges up the magnet, and when the switch is off, the energy in the magnetic core gets released into the load. So the demagnetization is happening with the load itself directly. So I don't need an extra demagnetization winding. So that is why in flyback we don't use a separate demagnetization winding. Is that clear? Forward converter alone needs it. Is that clear, Akshit?
Yes, sir.
Sir, one more question regarding DC-DC converters.
Yes, Arun, tell me.
Sir, when we are reading research papers, even with single switch DC-DC converters, there may be many modes, like 5 modes or 6 modes of operation. So, is it possible to visualize that multiple modes in simulation, or is it possible only to see in hardware?
No,
Like,
you can do it even in simulation. See, for example, if you take your buck converter itself, okay, you have one switch, one inductor, one capacitor, one diode, right? In the continuous conduction mode means that inductor there is always inductor current present. Then you have only two modes of operation, where the energy in the inductor is charging up and the energy in the inductor is charging down. These are the two modes of operation that will come for the two switch positions. Right. Now let us say, for example, you want to operate in the discontinuous conduction mode. Means there is a possibility of current flowing through the inductor and also the possibility of no current flowing through the inductor. Okay. So in which case you have charging up of energy in the inductor, charging down of the energy in the inductor, and the period of the duration when there is no current flowing through the inductor. Three modes come into play with one switch, single switch operation. Okay, so this is a discontinuous mode of operation like that. So this is the possibilities if you are talking of a hard switch. If you are talking of resonant mode or quasi-resonant mode, you will have few more modes which will come into the picture. But but all these things are simulatable even in your SPICE. Okay, if you are properly taking the values, you should be able to simulate them even in SPICE exactly. Clear, Arun?
Yes, sir. So this zero voltage switching, zero current switching, etc. Those
Yes.
things we can see in
You
LTS.
can see the waveform very clearly in SPICE. The SPICE results you can give you as close as possible to the practical results, depending upon how much non-idealities you have put in.
Okay, sir.
See, if you simulate the forward converter with demagnetization, that is a tricky thing. See, simulation demagnetization part means that there is a separate coupling for that one. The flux in the core has to get coupled to that, and when there is no flow of power either from the input to the output, only the energy which is stored in the core has to flow only through the demagnetizing winding into the supply. So that is a very interesting thing. And if you are able to get that simulation right, then you will get a lot of insight into the operation of the magnetics. So try this demagnetization winding or demagnetizing winding transformer with that included, and the forward converter topology, simple forward converter topology, you will appreciate the magnetics much better.
Sir, regarding that DQ transformation,
Ah,
in the assignment, there was a question regarding when we inject fifth harmonic into the supply voltage, what will be the harmonic in the D and Q outputs. So
yes.
I simulated and observed that there is a sixth harmonic coming in the D. But physically, what does it mean?
See, when you take in the DQ, so you have the vector is like a stick, right? So the stick is rotating in space. Imagine like that, visualize like that. Stick is rotating in space. So if the stick is rotating in space, if it is rotating in the anti-clockwise, okay, it is rotating in the anti-clockwise manner, then the angle that it is forming is called a positive angle. It's called a positive direction of rotation, right? And if it is rotating in the clockwise direction, then the angle that is subtended is a negative angle and negative direction. That's what we call them. Is that part is clear? Now, when you are incorporating, so you are having, let us say, 50 hertz. When you incorporate, when you see 50 hertz, and let us say it is this fundamental 50 hertz is making that stick rotate anti-clockwise 50, right? But when I introduce the fifth harmonic will make the stick rotate in the in the clockwise direction. It is in the opposite direction of rotation. that is the quality of the fifth harmonic, you will see that it is equivalent to as though it is rotating in the opposite direction. And let us say the original stick was rotating at 50 hertz in the positive direction. The other stick is rotating at 250 hertz in the negative direction. Then the relative distance between the two is 300 hertz, right? Relative speed between the two sticks will be 300 hertz, which is the sixth harmonic. So that is how sixth harmonic comes in to play. Arun, is it? Arun asked it, is it?
Yes, sir. Understood.
Exam pattern. Exam pattern will be mostly multiple choice type of questions. So, and it will be all from whatever the videos that has been taken. I think it must be, it should be easy, not to worry. Vinayak, which one you are asking?
No, sir. I am not asking. I am just saying thank you.
Oh, yeah. Sure. Great. No.
Good evening, sir.
Okay.
Yes.
Sir, this is Rahul Singh from MNIT Bhopal.
Ah,
Sir, actually, I want to know that you taught us in fourth week that to simulate space vector PWM for motor control.
okay.
But sir, I want to make SV PWM for inverter, PV inverter on MATLAB environment.
On what environment?
On MATLAB software, actually.
MATLAB. Okay.
Yes, sir. So, sir, please give some brief detail for. Actually, sir, I am comfortable
The
with.
same. See, the same thing. The same logic
Yes, sir.
is applied. Even see, whichever be the simulation software, we
Yes,
have so chosen that we wanted to choose a open source setting ecosystem. But even if it is a MATLAB, it doesn't change the dynamics of the equation. It is the same set of equations that you will use even in MATLAB. With
Actually,
MATLAB means Simulink. You will have to use Simulink for this one.
yes, sir.
Okay. So in Simulink also you have the library of tools. The most key tool in Simulink I will say is FCM, the function block. So you take that function block and inside that function block you can type in the code. You can type in the equation for the input-output relationship. Use that series of function blocks to develop that model, whether it is motor model or any other load, and have a triangle generator and your the reference currents or reference voltage comparison with the triangle generator to generate the PWM. But be careful in the sense that first you do everything only in the analog domain. Don't mix up the digital and the analog domains. After you are sure that the system is working in analog domain, then only introduce the sample and hold. There are sample and hold blocks in MATLAB which you can use to sense the analog signal, sample and hold, take it into a digital format. And that digital format, you compare it with the digital signals and digital controllers to get your PWM patterns. So when you, because that will very closely simulate what is going on in your microcontroller, and microcontroller is what is used everywhere, almost in any place. Either microcontroller or DSP is used. So you should not be doing a simulation only in the analog space. All the control portions should be in the digital space. So that sample and hold plays a major role in that one. So that you have to do it with caution, that there is settings given for sampling time and all those things. Is that clear?
Yes, sir. Thank you, sir.
Yeah. You can do the simulations, block diagram simulations with sample and hold also in ngSpice. I did not teach you that, but you can do the entire DQ controller, motor control, connecting to three-phase grid, all those things in block diagram itself. You can do in ngSpice by using analog behavioral modeling. So you will get an effect like Simulink. But Simulink is very, very friendly in GUI. That is, I agree that. But ngSpice engine is really powerful. Okay, guys, I think it is now 5. If you have any questions, you can always ask in the discussion forum. We will try to clear that doubt. Nice meeting up with you guys. And I wish all of you a very nice weekend, not only a weekend, very nice semester end also.
Thank you, sir.
Thank you.
Thank you,
Thank
sir.
you very much.
Thank you, sir. Thank you, sir.
Thank you.